Have you ever wanted to build a working ornithopter from scratch? Well, that's exactly what I did. This is the AT-47 Mantis. And it actually flies really well. What's even more surprising is that it isn't too far off from the real-life performance of an ornithopter. Maybe you just watched Dune and you want to pretend you're a pilot on Arrakis. Perhaps you're just interested to see if even building an ornithopter is possible. Either way, what brings us all together to watch this video is ornithopters. These unique flying vehicles have captured the hearts and imaginations of many designers. From the work of modern engineers attempting to mimic a bird's flight, all the way back to the conceptual flying machines from Da Vinci and Lilienthal. In the real world, only a few successful ornithopters have been made, as they are generally considered more complex than a general aircraft, as well as have reliability concerns. And you're probably thinking, no, Messier, you mean to tell me the giant oscillating death trap that flies by turning its wings into an out-of-balance washing machine is unsafe? And well, honestly, it's more possible than a lot of people think. Plus, the benefits an ornithopter design could provide are surprisingly cool. So let's briefly talk about what makes the ornithopter so special. An ornithopter works by flapping its wings similar to the motions of a bug or a bird to generate thrust and lift as opposed to a conventional propeller and motor setup. However, that's exactly the problem with the design. It involves a very unorthodox and inconsistent type of motion compared to any other mechanical device. That being said, a few ornithopters have been flown in real life. For example, rubber band-powered ornithopters designed to mimic bird flight have been thrown as models. The CIA attempted to make a bug-sized ornithopter for spying on people in the 70s, where its greatest weakness was just a gentle breeze. There has even been a manned flight with an ornithopter. And although it was limited in its capability, it showed some promising results. In the 30s and 40s, a few prototype ornithopters were built using a mechanical linkage to a piston engine. These ornithopters generated a flapping motion with the wings. The aeroelastic effects of the wing's movement could automatically generate thrust and lift as long as you could flap it back and forth. The problem we found with these designs back in the day was, surprisingly to no one, structural stability. For example, this French ornithopter built in 1937 failed because the wings collapsed during an air tunnel high-speed test, allegedly. In fact, the only working, flying, manned ornithopter was built by a guy named Adalbert Schmid when he flew his design a mere 900 meters. This ornithopter flew with a traditional wing setup, only relying on ornithopter motion for thrust, attaining a significantly low aspect wing as a result. With so many failures in its tests, it was looking more like an ornithopter than an ornithopter. Due to the overall impracticality of these designs, development was unfortunately never really pursued unless that design was specifically for mimicking the flight of a bird or insect. However, there are some advantages to the ornithopter design, and while most of the disadvantages prevent development, these advantages can have a significant impact on flight performance. First things first, efficiency. In terms of many real-life dynamics, this point is controversial. That is because it's nearly impossible to generate a realistic aerodynamic model for the constantly changing flapping aspect of an ornithopter's wing. At high speed, many ornithopters would theoretically experience significant drag, as the amplitude of the flap motion causes unnecessary drag in the vertical axis, thus slowing the ornithopter down. But, similar to the bird, ornithopters could exhibit superior low-speed thrust and maneuverability due to the flapping motion involving the entire wing as opposed to a singular propeller. Also, the ability to change incidence, wing shape, or other aspects of the wings could allow for quote-unquote hovering, or a form of VTOL flight at the right speeds. Lastly, in the events of amplitude and direction optimized for higher speeds, an ornithopter could theoretically be more efficient than a propeller aircraft. Due to the significant reduction of induced drag associated with high aspect wings designed to intentionally flutter on an ornithopter, whereas aeroelastic flutter on a plane is generally eliminated with lower aspects. As you all may know, higher aspect or skinnier wings means less vortices on the wingtips, which means less induced drag. So while it's not impossible, it would likely be very difficult to get an efficient ornithopter at higher speeds. So, all of this is cool and all, but how on earth do we design an ornithopter that can complete any of this, let alone efficiently? Well, that's just the problem. We are lucky enough to have a flight simulator, Flyout, where we can design this thing. Flyout is a very high-fidelity building game where you get to procedurally design your own fuselage, wings, engine, and just about everything in between, in pretty much perfectly realistic flight physics. Luckily for us, Flyout's aerodynamic model simulates each individual wing's movement separately, and with accurate physics, so the game's engine should theoretically be able to handle an ornithopter. And while I did experiment with my own ornithopter designs pre-release of the game a few months back, I couldn't really get them to fly in a controllable way, so I chalked it up to a failure for quite a while. That is, until I saw this. A user and YouTuber by the name of DecoFox had made a working ornithopter design that appeared to be under relatively good control. In this video, I saw him take off and generally fly an ornithopter under his own control with limited input from other control systems. So in order to make this video, I reached out to him to see how he did it. We ended up collaborating as he is making his own ornithopter video that should be released at the same time as this one. If so, expect the link in the description below. He and I ended up collaborating on various ornithopter designs for a few days, sharing all of our research and development news with each other so we could both build the best versions of our ornithopters. I found that his control system worked similarly to my pre-release control system, but he found a way to keep the vehicle in flight with good control. Here's how it works. In Flyout, you get a few parts known as joints. These joints allow any custom input to influence the angle at which it aims to rotate. Unfortunately, you can't exactly modify the spin rate in flight, so whatever it was, it needed to be constant RPM. On top of this, there was no significant scripting or programming in Flyout, so we needed to have a mechanical solution to the flapping mechanism. And a mechanical solution we invented. So, start by imagining a single one of these spinning joints. This one, for example, is spinning at 500 degrees per second. As we have a wing attached to it, it sort of spins like a propeller. So the first question I have is what happens if we put a second joint in this system that spins in the exact opposite direction? Well, the answer is pretty simple, it just doesn't move at all. I have that piece on the top there that's attached to the first joint, and that piece on the bottom, the main wing, that's attached to the second joint. As you can see, the motions perfectly cancel each other out. Now the question I have for you is, what happens if we angle this second opposing joint so it quote-unquote wobbles on its axis? Well, that's exactly how we generate the ornithopter's flapping motion in-game. By modifying its RPM or its motion in general, we can generate thrust and lift. On the wing itself, if we assign leading and trailing edge controls, we can also make the wings automatically pitch, yaw, and roll the vehicle, although a conventional aerodynamic control was also used on mine. The wings we use will be very high aspect and theoretically made of carbon fiber. The lightweight, high strength, and flexibility of carbon fiber allows for the aeroelastic flutter of an ornithopter wing, allowing us to easily generate the lift and thrust forces required for the ornithopter wings. Now that being said, there are still some problems with this design we need to solve. For example, there are no good ways to control the throttle with the vehicle, and the efficiency is very limited compared to our previous models due to the very high amplitude required to get off the ground. And how on earth would we do VTOL? On top of this, the dynamics between the flapping and stationary wing change so much that the vehicle is barely controllable like this. The lack of good throttle and maneuvering control were the bane of this thing's existence, and it was starting to look like another failure. And then, by some miracle, an idea came to me in a dream. This is not an exaggeration, the system literally appeared before me while I was dreaming that night. I asked myself, what if we were approaching this wrong the entire time? What if, instead of trying to modify the RPM of the vehicle with Flyout's limited control system, what if we tried to modify the amplitude? So here's what I came up with. Between those two counter-rotating joints, there was something I would call the collective, similar to how the helicopter's collective doesn't actually mess with RPM but still generates thrust. Instead, the joints would naturally sit directly opposed to each other. And as you turn the throttle up, the collective joint would increase the offset, allowing the throttle to increase in a more natural way. This would also allow us to reduce the throttle at higher speeds, getting back all that efficiency we would have otherwise lost. Lastly, adding some form of roll control to the collective also allowed us to control all axes in hover mode, including pitch, yaw, and roll. Lastly, it also allowed us to glide at zero throttle, once again increasing the vehicle's efficiency. This collective joint was revolutionary in Flyout's Ornithopter design, allowing DecoFox and I to construct the first Ornithopters with working controls on all axes of flight, as well as solving one of the most major efficiency problems with Ornithopters at higher speeds. Now in real life, obviously, it would be a little bit more mechanically complex than this. Systems similar to a helicopter swash plate could allow it to exist, but obviously it isn't as simple as just throwing a few joints together as we did in Flyout. But with our Ornithopter systems in place, it was time to start designing our craft. Our personal thopter here would be a 2-seat gunship design because I know how much you guys love my military builds, and I also promised to make a VTOL gunship sometime soon, so I am knocking out 2 birds with 1 stone. Also, it may be because I also watched Dune, and I kinda wanted Dune-style Ornithopter gunship. The initial design, however, included a twin-seat canopy, a relatively thin frame, as well as spots for 8 different blades. The pilot was designed to sit in the rear seat, elevated above the gunner for a full field of view to both pilot and gunner. The wings and control of this vehicle were surprisingly irritating. In Flyout, the physics of joints depends on the weight of each joint. Each Ornithopter wing needed 3 of these joints to function. If the joints were too light, the wings would act floppy. If the joints were too heavy, the aircraft would be incapable of flying. So I had to do a lot of tests to figure out the exact joint strength of each joint. The initial rotation joint sat around 75 kilograms or 165 pounds. The collective joint was the heaviest at around 100 kilograms or 220 pounds. The inverter joint, as it had no load on it, was the lightest at about 5 kilograms. Combined total, this weighed 180 kilograms for just the joint system. Add the carbon fiber wings and the weight exceeds 240 kilograms. There was a total of 8 wings on this vehicle, and the propulsion system ended up weighing nearly 2,000 kilograms alone. Add the weight of the power plant and it was even higher. Because of all this, I had to reduce the weight on the design wherever I could. Also, fun fact, our Ornithopter would be featuring a VTOL mode. Ultimately, in real life, I would want to vary the incidence or pitch of the blades to provide a vertical lift. But in Flyout, that would require a 4th joint and make our craft a lot heavier. So instead, I designed the leading edge and trailing edges of the wings as a sort of flap that I could control in VTOL. On top of this, instead of varying the pitch to generate commands for roll and level flight, they would also act as ailerons on the wings and modify their direction. Once again, I would probably want to do this with variable incidence in any scenario where it does work, but I actually made a variable incidence testbed with 4 joints and it was just too heavy to fly with that 4th joint. Moving on from there, while the power plant of the vehicle couldn't exactly help me with the actual motion of the joints, what it could do was help me with the control. I added a big old tail fan as well as a horizontal and vertical stabilizer setup to help me with high-speed control of the vehicle. The fan, while not required, gave me a far better control of the vehicle at low speeds and therefore made the whole platform just a lot more stable. On top of this, it just sort of looks cool and gives the turbines something to do other than just idle. This is because in Flyout, the joints actually don't have a physical power response. There is no joint in the game, unfortunately, that doesn't work under its own magical space power, and there is no way for me to actually hook it up to an engine. So technically speaking, the wings and the entire craft could fly without an engine, but I obviously didn't want to do that because it kinda seemed a little dumb. Moving on from there, the Ornithopter also featured a basic, retractable 3-point landing gear system. My initial tests had shown that this vehicle can fly over 250 knots indicated and up to Mach 0.7 at altitude. Because of this, every bit of aerodynamic streamlining was required. Fixed landing gear, or skids as most helicopters have, would not be capable of the drag reductions I was looking for. This is why I chose a 3-point retractable gear design. Plus, unlike a helicopter, this thing has the ability to taxi on the ground. On the nose of the vehicle, I modeled a fake, of course, targeting pod. This would be great for its high speeds and altitude, so the gunner could accurately guide precision ordnance into a target. This consisted of 3 optics as well as the ability to swivel it with the arrow controls on the keyboard. It was somewhat inspired by the AH-64 Apache's targeting ball while also taking my own creative liberties with it. Due to the high top speeds of the vehicle previously mentioned, I also built it with retracting weapons pods or an internal weapons bay. These 2 bays on the side of the vehicle extended outwards when deployed. allowing the operator to shoot rockets such as a conventional helicopter or mount other air-to-ground ordnance such as bombs or missiles that needed to be dropped. Later in the design phase, I also added detachable hardpoints to the side of the vehicle because, let's be honest, it doesn't matter all that much. I kept them off for the majority of the time, however, because I just liked the way it looked with the internal bay. Lastly, in order to really make this design look good, I added some minor details to show you guys how an ornithopter may look while it's actually in service. For example, I added a MAW, or Missile Advance Warning, to the side. In real life, MAW is a simplistic IR or radar seeker designed to detect and warn the pilot of incoming missiles with passive seekers, such as IR missiles like the AIM-9, R-73, or any man-pads. As this was a gunship, protection from man-pads or man-portable air defense systems was crucial to vehicle survivability. This, combined with the low-temperature turbines and countermeasures to the sides of the vehicles, helped it protect itself. Modern man-pads and missiles, however, can't just be fooled by flares. On board many of these missiles, IRCCM or infrared countermeasure systems are very common. These systems usually involve predictive targeting or variable field of view seekers to predict or altogether ignore flares, or any infrared countermeasures. This is sometimes also referred to as signal processing. The ability for these missiles to see the entire image, and the ability for onboard computers to process which signal is the aircraft has made modern missiles a significantly larger threat. Because of this, the MAW systems and flare positioning were designed to fire forwards and have extra advanced warning. Think of it sort of like my own IRCCCM, an infrared countermeasure. So you know what, we'll definitely be safe until the next guy comes out with an IRCCCM system. When that comes out, we'll be sure to develop an infrared countermeasure system, or IRCCCCM. Wow, I'm confusing myself with this. You know what, we should probably just use a different name by then. From there, we also added a few basic helicopter utility features, such as the cable cutters you see that prevent cables from hitting the helicopter rotors, as well as a few general aviation features. This includes formation, nav, strobe, beacon, and landing lights on the vehicle, as well as antennae for GPS, VHF radio, and the special military UHF radios. After adding some nice hand-painted textures to the panels, weathering, and a cockpit that may just be ripped assets from my previous aircraft, we were finally ready to fly out. The Mantis was complete. But before we fly, there was a problem. Of course, I have to give Flyout credit, it does a lot and it's amazing that the physics engine can even handle something like this. However, what really unnerves me about the Flyout Ornithopter is that they generate no sounds. So I made a little montage or cinematic with the vehicle for the end of the video here. And I wanted to let you guys know that I designed my own custom sounds for the Ornithopter using some samples online and some that I took in real life. I hope you guys enjoy it, and I'll see you in the skies.
An attacking force has mounted itself northwest of the airbase. All units scan for targets bearing 250. Multiple air defense units spotted and engaged by ground forces. Exercise caution and good luck.
Dragonfly 1-1, runway 35, cleared for takeoff.
Contact spotted, 290, 10 miles.
Base, que apontamento a 37. Detectamos bug a 116 por 15, 600 metros, vindo em nossa direção. Aguardamos instruções, câmbio.
Missile, 6 o'clock, let's move.
Missile evaded. Re-engaging target.
So here it is, the AT-47 Mantis. Lightweight, nimble, and deadly. Let's talk a little bit about its stats. The Mantis can climb nearly straight up, having a just about 1-to-1 thrust to weight at cruise speeds. While it barely generates any thrust at low speeds and even feels sluggish, that's because the Ornithopter has a very specific power band where it generates the most thrust. All in all, it has an amplitude of about 27 degrees total, a 13.5 degree upstroke and downstroke. It is rather limited with its weapons due to the weight, but it otherwise flies very well. In hover mode, it can get a little bit shaky, but I guess it works. I shouldn't really call it a hover mode, however, as it only reduces total velocity to around 10 meters per second forward at any given point in time. In cruise, the Thopter is surprisingly smooth, showing on the accelerometer of barely being shakier than normal flight. You turn on the quote-unquote engines by pressing the I key and control VTOL through the flaps. If, and only if, you fly this thing gently and don't push it too far and try and stall it, it flies super pleasantly. It turns well and performs smoothly, which leads me to my conclusion. Ultimately, while I love ornithopters and they fly surprisingly well, I can't say that they're really possible vehicles. The vibrations, the stress, the complexity, there really isn't much reason to build one. So while it's a super cool and surprisingly pleasing to fly vehicle, I can't really see any standardized applications of these things coming around unless there is some massive breakthrough in ornithopter technology and safety. I really hope you guys liked that little montage I had there, although it is admittedly completely unrealistic. I can point out the amount of inaccuracies in that in like mere seconds, but it was really meant to be fun and cinematic more than it was realistic. Thank you very much to the voice actors who participated as well. The credits for these voice actors and their excellent performance will be in the description. And of course, if anyone cares to download this thing, feel free to check it out on my server where I will upload a zip file post-release. I hope you guys enjoyed, and if you want more Ornithopter content, feel free to check out DecoFox's video as well. See you all on the next one, and goodbye.